Hello and welcome to Empowered Learning. This is the second video in the Logic Theory video series. And in this video, we will go over some more truth tables. In particular, we'll practice building truth tables. And at the same time, we will see the equivalent of DeMorgan's laws within logic theory. We are also going to look at what we call valid arguments and fallacies and the different type of structures that we have. And we're going to see truth table wise why we call a valid argument, and why we have some structures of a compound statement called a fallacy. Okay? And then the last thing that we'll do is we will talk about quantifiers. So once we're done exploring all the truth table stuff, we will talk about quantifiers and how we use that in logic. So let's go ahead and get started. So first thing that we want to do is just build these four truth tables that I have here. So just going to scroll up a bit and we will just build them. And then after we build them, we will see what it is that we need to see. So to start off, if you watch the first video that I've made, then you understand why I'm going to start off here by true, false, and true, true, false, false. And so now, to be able to build this, we pay attention to our grouping symbol here. So we have to do everything that's inside the parenthesis first before we execute this negation connective. So we know that P and Q is only going to be true if both P and Q are true. So here we know that this particular column would have to be true with 3 falses. And then, of course, the negation says that we need an opposite of whatever's in here. So that's going to be false, true, true, true. Okay. Now, if we do this again, but we do it with not P or not Q, then, of course, we start off the same way. True, false here, and true, true, false, false there. We do the opposite of P, which is false, false, true, true, and the opposite of Q, which is false, true, false, true. And so now, if we OR these two columns together, OR means that if at least one of these two statements is true, then everything is true. So we know that we'll have false for this first one since both are false, but for the rest of these, they end up being true. So if you notice, these two columns here are exactly the same. So what that tells us here is that logically speaking, we know that the negation of P and Q is equal to the same thing as negating P on its own and ORing that with negation of Q. So let's move on to the next two. So once again, we start off with true, false, and then true, true, false, false. And here we'll do the opposite of P, which is false, false, true, true, and the opposite of Q, which is going to be false, true, false, true. And then in this case, we have to AND these two statements together. And interprets to the only time that the entire statement is true is if both statements here are true. So we know that this would be false, 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 and true. Okay. Doing the same thing with example D, we need to come up with our P and Q first, and then after that, OR those together, and then take the negation of that. So true, false again, true, true, false, false. And so now, if we OR these together, OR means if at least one single statement P or Q is true, then it means everything is true. So we know that we have T, or true, 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 false. And then the negation of that is false, 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 true. And again, we see that these two columns are the same. So this tells us that not P ANDed with not Q is the same thing as doing the negation of P or Q. And so these two identities, as if we want to call them that, within logic, these are what are called the DeMorgan's laws. And so if you've watched my video on set theory, then you've seen that we've also done some DeMorgan's laws for set theory as well. And so these mimic that, but in the logic world. Now, the reason why DeMorgan's laws are important is because if we're trying to model something logically, especially, let's say if you're an engineer and you're trying to make some type of digital circuit, one of the things that you use is Carnal mapping to be able to do that. And so what a Carnal map is, it just lays out all the possibilities that you have, and then you logically try to reduce the number of connectives that you have in your logic statements. Because as an engineer, a connective is just like a device. So they actually have digital logic devices that they call AND gates that do that do what AND does in logic. Okay, it only allows a signal to go through that particular device if and only if this is true and that is true, so your result here can be true. And of course, if true is power on, then you can look at this as power on, then you go through power on. If you had a situation where if you had an AND gate and you had power on here but power off there, then the result would be power off. And again, so DeMorgan's laws help us to be able to reduce the amount of connectives that we have. And just as an example here, you can see in this form of this statement, we have 1, 2, 3 connectives. We have 2 tilde signs and 1 AND sign, TP as I like to call it. But here you see we only have 2 signs, 1 tilde and 1 OR connective. And so by doing that from a device standpoint, if I can design a circuit that has, for each block there, only 2 connectives or 2 devices instead of 3, then I've just saved 33% in cost because I've reduced everything I needed to do by 1 device. Okay, so that's just one example why DeMorgan's laws are important. Now we have one other truth table that I want to do on this particular page before we move on to the next set of truth tables that we want to do. So let's go ahead and build this. So we have true, false, and true, true, false, false. And we're going to do the opposite of Q, which is going to be FT, FT. And then we're going to do P or Q. So we know that's going to be true unless both P and Q are false. We do the opposite of that, which is going to be false, 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 true. And so now after that, we start to build our next part. So here we know this is a biconditional statement. We have basically did what we needed to do to build this portion of the biconditional statement. Now we're going to build this portion. So within the grouping symbols, we need to do not Q first. So we already have that here. And so now we're going to do not Q and P. So what I'm going to do to make sure that I'm not confused, I'm just going to rewrite not Q over to the left of P so that we can read it correctly. So not Q is going to be F, T, F, T. And so now when we look at this, false and true is going to be false. True and true is going to be true. False, false is going to be false. And true, false is going to be false. Okay. And so now that we have everything that we need to build here, then we take these two columns and we're going to do the biconditional statement. And of course, if we remember the truth table for the biconditional statement, I'll redo it here so that we remember that. We know that the only time that, let me finish writing this. So the only time that the biconditional statement was true is if both P and Q were true or if both P and Q were false. So we have these situations here. So now when we read this biconditionally, this is going to be true. Biconditionally, that's going to be false. Biconditionally, that's going to be true. Biconditionally, that's going to be false. Okay. So we want to see all the given outcomes for the biconditional statement in E. That's how we would do it. All right, so let's move on to some more truth tables. All right, so the next set of truth tables that we're going to do them because they represent arguments. And so we're going to see that some of these arguments are called fallacies. Some of these arguments will be called tautologies, okay? Or we're going to say that they are valid arguments. And so what I want to do first is kind of show you where we're going. So I'm going to go a few pages up to kind of describe where all this comes from. And then from there, we're going to do the truth tables for some of these. Okay, so what we're going to be doing truth tables for here are what we call valid arguments and invalid arguments. And so I first want to make sure that we define what an argument is and what a fallacy is. And so an argument is a statement that uses a set of facts or assumptions, which we also call a premise, to support some type of conclusion. Okay, so again, it's a statement that uses a set of facts or assumptions to support a specific type of conclusion. Now, what a fallacy is, it's an argument failing to make a compelling case for its conclusion. In other words, it has some type of error in its reasoning. Now, how we are going to know whether a particular argument is going to be valid or not is that in all of its situations, how the statements are structured within the argument are going to be such that in all cases we end up with a true statement. Okay, and so another way of saying that we end up with a tautology. Okay, whenever we say it like that. Now, if we have a case where we have at least one false entry within our last column for the truth table for any of these arguments, then we say that it is a fallacy. And so how we're actually going to interpret this is as follows. So for instance, the law of detachment. So how we read this is that if we have some argument that says if P, then Q, and then along with that, and we know that P happens, then the result is, of course, all this happens here, then the result is that Q happens. So if P, then Q, ANDed with P happens, then the result is that Q happens. So the way that this is structured, the law of detachment, is one of these cases where we have a valid argument, meaning that we end up with, in the last column when we do the truth table, we have true for all of them. The law of contra position, law of syllogism, and a disjunctive syllogism does the same exact thing. Now, the fallacy of the converse lets us know that when we make a converse statement, that isn't necessarily a valid argument in all situations here. And so for this one, if we were to interpret it, we'll say if P, then Q again. And then along with that, we'll say and if Q happens, then the result is that P happens. And we'll see that in at least one scenario that this is going to be come out to be a false statement whenever we do the truth tables for it. Okay? So I will do the truth tables for one of these, from beginning to end, that is a valid argument, and then I'll do one of these for the case when we have an invalid argument, and then for the rest of those, I'll just fill it out and then show it to you so that you can look at it and see if you can get it yourself. All right, so what we're going to do here is first work on the law of syllogism first, and then after that, for the rest of these that I have for you, I'll just sort of fill out everything, and you can just kind of look at it to see if you get the same thing there. Okay? All right, so for the law of syllogism, we start off and we have three separate statements. We have a P, we have a Q, and we have an R. So this time we know we need to have 2 raised to the 3 rows, which is 8. So we start off here in the R column, true, false, true, false, true, false, true, false. So we repeat true and false 4 times. In the Q column, true, true, false, false, true, true, false, false. And then in the P column, 4 times. True, 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 false, 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 false. Okay? And so now from there, what we're going to do is just form our next column here, which is the conditional statement. Of course, we're going to read if P then Q. So we know that if P then Q, or the conditional statement, is true for every situation unless P is true and F is false. In other words, the first statement is true, the second statement is false. So if we're reading here, true and true is true, true and true is true, true and false is false, true and false is false, false true is true, false true is true, false false, and false false both are true. Now, if we're going to do if Q then R, then we read these 2 columns. And so again, only time that we're going to put false is if the first statement is true and the second statement is false. So we have we have true, then false, true, 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 false, true, true. And so now from here, we're going to AND these 2 columns together. So when we AND them together, we know that the only way that this column is going to be able to have a true in one of the scenarios is that both first statement and second statement are true. So this will be true. We've got false, 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 true, false, true, true. So what we've done up to now is followed the order of connective or order of operation to be able to do everything inside of here. So the next thing that we're going to do is work on what is if P then R. Okay? So in this case, we need to look at this column and this column. So let's be very careful when we do that. So to do this, if we say true, true, it's going to be true. True, false is going to be false. True, false is going to be false. True, false is going to be false. False, true, false, 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 true, and false, false are all going to be true. So these last 4 are going to be true statements. And so now, to build everything, now we know that we're going to take this column and this column, and use it as our first and second statement for the conditional statement that we end up with. And so when we see this, we'll see that we should get true in every scenario. So we have true and true is true, false and false is true, false and false is true, false and false is true, true and true is true, false and true is true, true and true is true, and true is true. So we see here that in every situation, we end up with all situations being true. And so by that, we know that this is what we call a valid argument. Okay. All right, so let's move on to the next one. And so this is the law of contra position that we saw and the law of detachment. So I'm going to allow you a second to look at that. You may want to pause the video and write this down and then see if you can work it out on your own. And so what I'm going to do is I'm actually going to do the same thing. I'm going to work out both of them and then show you what I end up getting. Okay. All right, so for the law of contra position, this is the corresponding truth table for that. And again, as you see in the last column, we have all T's there, meaning that all situations, all ways that we can structure this argument, whether P is true or false, ends up being a valid argument. So with the law of detachment, see that we have the same thing. All right, so we'll go ahead and move on to example D. So for example D, I didn't show you this one, but this is what a disjunctive syllogism looks like. And the way that that argument is structured, we see that that also is what we call a valid argument. So in that case, again, we have all T's in the final column. So you may want to write down this one and try it out yourself to see if that you get the same thing. So now let's go to the fallacy of the converse. So we'll build this one from scratch, and then afterwards we'll do the fallacy of the inverse as well, so that you can see that in these cases we have at least one of our outcomes or one of our rows in our truth table that ends up being false. All right, so let's go ahead and build the fallacy of the converse truth table. So we'll start off by listing again the column for F and C, and see we've already done that here. And we'll do the conditional truth table. So we know that the only time that if C then F is going to be false is whenever we have first statement being true, second statement being false. So every other situation is true. So we'll have true, false, true, true. And then we have this statement ANDed with the F statement. And of course, the only time that we have an AND statement is true is when both are true. So we have true, true here. And we have false, false, so that's false. True, true. False, true, which is false. So now we copy down C again, which is true, true, false, false. And so now from there, when we do the conditional statement for everything that we have here, which is in this column, and C, we see that we end up having true and true is true, false and true is true, true and false is false, and false and false is true. And notice here how we have it, that one false outcome. So this is what lets us know that this is an invalid argument. Okay. Now we'll go ahead and move on to the fallacy of the converse and show that we end up with at least one false statement there as well. So again, we'll start off by columns, T, F, T, F. Go and bring these down some. And then T, T, F, F. And then conditionally, we know if P then Q, both are true is true. First is true, second is false, and then anytime it starts with false, then it's true. For the negation column for P, we just write F, F, T, T. And then after that, we're going to AND these two columns together here, because this is the first column, that's the second. And so when we AND them, the only time we get true is when both are true. So we have false, false, and true, true. And then after that, we need to take this column and we need to AND it with a not Q column. So we haven't done that yet, so I'm going to make some room to do that now. All right, so we've made a column for not Q, and so we'll just do the opposite of what we see in the Q column. So it'll be F, T, F, T. So F, T, F, T. And then we will take these two columns here and look at them as the statements of a conditional statement. And of course, we know false, false ends up being true. False, true ends up being true. But here we have true, false, which ends up being false. And we have true, true, which is true. And again, we have at least one false outcome. So again, this is an invalid argument. And so by doing this, one of the things that we see is it really doesn't matter what the statements are. What matters is how everything is ordered and structured in the actual argument. And so we could, say P is monkeys fly on the moon. Q is, the sun is red. It really doesn't matter. So, but if we state what we say in such a way to where it meets the fallacy of the inverse, or this other one up here, the fallacy of the converse, we know that we're going to have a false statement there. But for some of the others, like the disjunctive syllogism and the law of contra position, no matter how we say it, is going to end up being true. And so that's sort of the beauty in logic. So let's move down here. So we know that in examples A through D that we did, the last column was all T's. In other words, it was true. And in examples E and F, we had at least one false, or at least one F in it. And of course, we know that this means valid argument when we have the situation, and here when we have at least one false outcome, that's going to be an invalid argument. All right, so to conclude this video, I wanted to touch a little bit on quantifiers. And so we know that sometimes in a statement there are keywords or phrases called quantifiers that tell us how many of something are of a certain type. So in this first blank here, we need to have quantifiers, and it tells us how many of something are of a certain type. Now we have two types of quantifiers. We have universal ones and we have existential ones, depending on how you want to say that word. Now, for a universal quantifier, universal quantifiers state that all objects of a certain type satisfy a given property. Okay, again, so universal includes everything. So it says all objects of a certain type satisfy a certain property. And we know that we have a universal quantifier when we see words like all or every is used in the statement. For existential quantifiers, we know that they state that some of the objects in a certain type satisfy a given property. And of course, we know that we know we have an existential quantifier when we see words like some, or there exist, or there exist at least one that are used. Okay? So now what we want to do is determine which of these statements here have universal or existential quantifiers in it. So here we see that we have some drivers qualify for reduced insurance rates. So that's going to be an existential quantifier because it uses words like use the word some. For B, since we see the word all in there, all athletes must weight train, that's going to be a universal quantifier. For C, it says every triangle has an interior angle sum of 180, excuse me. And so the word every lets us know that we are experiencing a universal quantifier there. And so for D, it says for the function y equals 1 over x, there exists at least one number that does not satisfy this equation. Okay? And so the phrase there exists at least one real number, at least one rather, that lets us know that this is an existential quantifier. Okay. Now, in addition to universal and existential quantifiers, we also can negate these quantifiers as well. And of course, we can negate a quantifier by just replacing a universal phrase with an existential phrase. And to negate an existential quantifier, we do just the opposite. We replace an existential quantifier with a universal one. So I have a few examples here based off of what we just got through doing to sort of illustrate that. So if we negate statement A that we saw earlier, instead of saying that some drivers qualify for reduced insurance rates, we say that all of them. And for B, instead of saying that all athletes have to weight train, we would say some athletes do not have to weight train if we're going to negate that quantifier. And then in the last one, we said that for every triangle has an interior angle sum of 180. Instead of saying that, we can say that there exists at least one triangle where the interior sum is not 180 degrees. And so that is how we negate quantifiers. And so this will conclude the second video within the logic theory series. The very, I should say not the very last, but the next video that I'm going to do in this series is going to talk about just alternative forms of conditional statements, as well as what a syllogism is, which is another way of saying a valid argument, and how we define that. And given a certain argument structure, we can determine whether the argument is valid or not by using Euler diagrams. Okay? And that will conclude the series on logic. So thank you for checking out this video, and I hope that this helped, and make sure to check out part 3. Thanks.